Hello. Good morning, Dr. Sabrina.
Good morning.
Good morning.
Good morning.
Good afternoon for you.
Good afternoon. Good afternoon. So, we'll be starting within 2 minutes, 2-3 minutes.
Yes. Yes.
Okay. Okay.
Please let me know when I can start.
So we'll start within 2 minutes. 2 minutes.
Okay, I'll wait. So I see that not all the students are online yet, so I'll wait.
Professor Sabrina, we can start.
Okay. Okay, perfect. So, good afternoon again, everyone. And today we will continue on the passive radars. Yesterday we have seen the geometry of the bistatic systems, the importance of some parameters like the bistatic range, bistatic Doppler frequency. Then we have seen also the range resolution, the frequency resolution. Then we looked also at the ambiguity function, the bistatic ambiguity function. And we have seen that it changes depending not only on the waveform, but also on the geometry. We know that the monostatic ambiguity function depends only on the waveform that is transmitted by the radar. In the bistatic case, the ambiguity function depends not only on the waveform but also on the geometry. So the geometry in the bistatic system is quite important. But we have seen also that since the waveform is not designed for sensing purposes, sometimes it is not ideal for radar, and it can present high side lobes or peaks that must be cancelled before using the signal for sensing purposes. We have seen also the main source of opportunity from the FM radio stations to the DAB, the VBT, Wi-Fi, and so on. And we have seen also that some system uses multiple sources of opportunity, not only one at the same time, choosing the best signal. And it is also possible that in the same area there are multiple transmitters, so multiple source opportunities with different geometries. So the system can at least avoid the bad geometries. We have seen that when the target is crossing the baseline between a transmitter and a receiver, then the receiver, the radar, loses the resolution and the capability of detecting the target in a specific range position. So this kind of geometries must be avoided in order to detect correctly the target, detect and then track also correctly the targets. Now, today we will look in more details into the signal processing algorithm in the different blocks of the passive radars. The main blocks of the passive radars are sketched in this slide. So first of all, we recall that there are two different channels. One is the surveillance channel, and the other one is the reference channel. In the surveillance channel, ideally, we want to receive only the scattering, so the echoes from the targets, and the noise, thermal noise. But actually, we receive also the direct signal, so the signal coming from the transmitter, that normally is quite strong, and it is much stronger than the echo coming from backscatter from by the targets. And then there is also the clutter that it is always present in all the radar systems. Then, ideally, in the reference channel, we would like to have only the signal, the reference signal. But in this case, the reference channel would be clean, but actually there is also noise and possibly also clutter. So all these different terms should be considered in the detection of the targets, so in building also the detectors. Now, let's start with the different blocks. Since the main block is the cross-ambiguity evaluation, we will start with this one. Then we will detail what the disturbance cancellation is, the signal conditioning is, and also the cipher detection, and of course the tracking. I mean, the tracking is quite similar to what is done in the monostatic radars. So we will see only a few words, an example more than that. So let's see the cross ambiguity function. Practically, the cross ambiguity function evaluation. So the cross ambiguity, because it is between the surveillance signal received in the surveillance channel and the reference signal. So this calculation of the ambiguity function corresponds to mesh filtering, and we use this calculation to have an estimate of the bistatic range and the bistatic Doppler shift. So this is quite important. Um, the problem is that we have a long integration time, and we have multiple signals that are multiplied, multiple copies of the reference signal multiplied by different Doppler frequencies shifted, and multiple Doppler frequencies in order to build the cross ambiguity function. That's why this operation in terms of computational burden is very costly. So we need to find efficient ways to calculate the cross ambiguity function. We need efficient implementations. So let's look at the cross ambiguity function. We have seen already that we have the surveillance channel, so what we receive from the targets, and then the reference channel. The reference channel is shifted in multiple Doppler frequencies, the frequency of our interest, and then each reference channel multiplied by, shifted by the different Doppler frequency on a log integration time is correlated to the surveillance channel. And then we can build this three-dimensional quantity that is the cross ambiguity function. And we have on one dimension, on one axis, the Doppler, bistatic Doppler frequency, and on the other, the bistatic range. Of course, from this bistatic Doppler frequency and the bistatic range, we needed to estimate the real velocity of the target and the range of the target, so the distance of the target with respect to either the receiver or the transmitter. So the typical CPI, the coherent processing interval in a passive radar is much longer than in active radars. So we observe the time for the target for a long time. And in this way, we have a very fine Doppler resolution. We have seen that in some system, the integration time is even some second long. And we can have also a large integration gain. That is quite important, because you have seen that actually the signal to noise ratio with a short integration time would be too low. We need a long integration time for increasing the signal to noise ratio, so making the signal detectable. And since we have this long integration time, we have this very high Doppler resolution, then we can even see the micro Doppler. So we can perform micro Doppler analysis, we can see the changes in the Doppler, very fine changes in the Doppler. And we can also, for instance, see the flashes of the helicopter rotor blade. So it means that with passive radar, we can look also at for instance, the movement of the human being, or the movement of the different parts, the different elements of the same object. This is not always possible with the active radars, because the integration time is not so high, and then not always is possible to see the micro Doppler. Of course, there are active radars with very high resolution in frequency that can be used for micro Doppler analysis. Now, let's look at the more in details into the cross-ambiguity function evaluation. Now let's go back to the definition. So X is the ambiguity function, and tau and Ft are the Doppler shift, so the frequency, the bistatic Doppler frequency, and tau is the bistatic time delay. So we need to estimate from the ambiguity function this delay tau and this Doppler frequency Ft, so we can locate the target in some position, and we can estimate the velocity of the target. We have seen the definition of the ambiguity function, that is the modulus of the integral, the product of the surveillance signal times the reference signal delayed and shifted by the Doppler frequency Ft. So we have seen that it is the output of the meshed filter when, of course, the input signal is delayed and shifted in frequency. And actually, the integral is not between minus infinite and plus infinite. This is the definition, but the integral is limited on the coherent processing interval. But we have said that this coherent processing interval in many cases is quite long. So the calculation of the cross-ambiguity function is not done in the analog domain, but of course this is done in digital domains. So we use the sampled signals. It means that before, of course, building the ambiguity function, the analog signal has been sampled. Keep in mind that we work with the complex envelope, so we work with the I and Q low pass component of the signal. And then the integral actually is replaced by sum, and the sum is over all the samples, capital N samples of the surveillance signal and the reference signal. And as you can see, we have two different indexes. One is L. L is the index for the time delay sample, and M is the index for the Doppler frequency. So you see that actually L corresponds to the a time bin, because we have sampled with a Fs sampling frequency the samples of the signal, surveillance and reference signals. And then the number of integrated samples is, of course, t int, so the coherent process interval t, times fs, that is the sampling frequency. This n could be very, very high depending on the integration time, so the coherent processing interval, and also the sampling frequency. So actually, this ambiguity function becomes the modulus of the sum of the product between the surveillance sample, the surveillance signal, and the sampled, delayed, and shifted in the frequency of the reference signal. Okay, so we have all this product that must be performed by our system, and then we need to do all these sums for all value of L and for all value of M. You understand that the number of calculations that we need to do is quite high. So if we implement directly the definition that we have here, it could take a long time and to calculate all the values of the ambiguity function. So we need to find an efficient way to do it. So actually what we obtain with this sum is the 2D map, and the dimension is n sub t times n sub f. So in the delay dimension, we have n sub t samples, and in the frequency dimension, we have n sub f samples. So n sub t is the number of time beings of interest, n sub f is the number of Doppler beings of interest. So without oversampling, so if we sample only the enough samples without increasing the sampling frequency, then you see that n sub t, so the number of samples, depends on the sampling frequency, and depends also on the maximum delay that we would consider. And the maximum delay is given by the maximum distance that we want to cover, the maximum bistatic range of interest divided by C. Now, what about the number of Doppler beings of interest? It depends, of course, on the maximum bistatic velocity of interest. And then we have that the number of targets in number of samples is practically 2 times the maximum Doppler frequency that we want to consider, times n divided by fs. So as you can see, there are the number of samples can be very, very high. Now, the direct implementation, or direct means using the equation, the sum equation as it is, without implementing any specific algorithm, means that we have n times n tau plus 1 times nf complex multiplication plus a certain number of complex sums. So this operation would be very time consuming, and I mean, we need, as I already said, we need to find some efficient algorithm to calculate it. Now, the effective and efficient calculation of the ambiguity function is related to the FFT and the inverse FFT algorithm, because these reduce the calculation burden. why we want to consider the FFT and the inverse FFT algorithm? Because we know that these algorithms are particularly fast and efficient, and particularly if we use power L02 in a number of samples for both the FFT and the inverse FFT algorithm. Why we can use these algorithms? Because the ambiguity function actually is practically a correlation, or we can interpret it also as a convolution. And you know that the convolution in a frequency domain corresponds to a product of Fourier transform. And then if we can operate this convolution in a frequency domain, we can do the FFT and then go back to the signal on time through the inverse FFT algorithm. Actually, this is the normal way that in many cases it is applied for making efficient convolutions. So generally we pass to the frequency domain. So we calculate the product of the Fourier transform, and then we invert the Fourier transform to go back to the time domain. So something similar is performed here in the calculation of the ambiguity function. Let's see how. So one of the approach is to observe that actually x, so the ambiguity function, can be viewed as a discrete Fourier transform, DFT, and then it can be calculated using the fast Fourier transform. Let's go back to the definition. As you can see here, there is the exponential term e2 minus j2 pi mn divided by n, capital N. And this is the base of the discrete Fourier transform. So we can reinterpret this sum as a kind of Fourier transform of the signal that is S surveillance times S ref. And then we can perform this Fourier transform through the FFT algorithm. So let me explain. So if we define this new signal YL of n as the product between the surveillance signal in N and the conjugate of the reference signal in N minus L. So this is what appear here in the equation of the cross-ambiguity function. Then you see that these Fourier transform of the signal. Then we can calculate the ambiguity function, the cross-ambiguity function, as the fast Fourier transform of the signal YLN. Okay, so of course we do it for each n and for each n. Then we need to define all. So let me explain a little bit better. So as you can see, this signal depends, y depends on n. So it is a sequence of values, but it depends also on L. So we have multiple sequences, one for each value of L, so for each delay. And then we need to calculate the FFT of each of these sequences, okay? So for each value of L, we calculate the FFT. And in this way, we build the cross ambiguity function. There are another approach. So why this approach is particularly efficient? Because the fast Fourier transform is an efficient and fast algorithm. So if we can apply it directly to the signal, then the calculation of the cross ambiguity function will be shorter in time. Then let's look at the other methods to calculate, efficient methods to calculate the cross ambiguity function. One of these ways is to go back to again to the formulation and consider that we have two different signals. One is the surveillance signal, the other one is the reference signal times the exponential part. So we have two signals, one S surf and the other is S conjugate ref times the exponential. Well, in this case, actually, with this interpretation, and you see that the signal ym2 depends on n, but depends also on m. M is the index of the frequency. Then in this case, the sum can be interpreted as the correlation between the signal y1 and the other signal ym sub 2, okay? But the correlation, okay, or convolution can be, the cross correlation can be implemented in an efficient way, passing first to the frequency domain and then making the product between the two FFT of the signal y sub 1 and y sub 2. And then once we do this product, we are in the frequency domain, then we invert. So we go back to the time domain through the inverse of the FFT, and then we go back to the X. We can calculate X, so the ambiguity function. So summarizing, there are multiple ways to calculate the cross ambiguity function in an efficient way. And remember that the passive radars continuously calculate this cross ambiguity function in order to estimate the Doppler frequency of the target and the range position of the target. Must be implemented in an efficient way. There are multiple ways. One is to interpret the cross-ambiguity function as the Fourier transform of the product of these two signals. So we needed to build sequences of YL and make the FFT of all these sequences, and then we build the cross-ambiguity function. Or we can interpret the cross-ambiguity function as the correlation between two signals, y sub 1 and y sub 2, and then we implement this correlation between these two signals, first going into the frequency domain through the FFT, because the correlation becomes a product between the fast Fourier transform. And then we go back to the original domain through the inverse fast Fourier transform. Again, here the number operation is optimized to the inverse fast Fourier transform and the fast Fourier transform operation. Okay, so this is the way we calculate the cross ambiguity function. Now, before calculating the cross ambiguity function, we need to clean the signal, because we have seen that actually in the surveillance signal we have together with the echo coming from the targets, if there is some target, we have the clutter and we have also the direct signal, so the DPI that is quite strong and much stronger than the signal coming from the targets. So there are multiple things that we need to do before the cross-ambiguity function. As I told you, we have this direct impact interference. So we have touched upon some methods to to cancel or at least to limit the interference of this direct impact. Some of them are related to the antennas. We have seen also that it's possible to put kind of screen between the transmit the reference antenna and the surveillance antenna, but this is not always possible. Then we can use directional antennas or digital beamforming. So in this way, we could put some null in the direction of the reference antenna in order to cancel the direct path interference. But actually, you will see that in the majority of cases, we use a signal processing algorithm to cancel or to limit the DPI. Then there is also the clutter and together with the thermal noise, but the thermal noise is really unavoidable. It is present in all the electronic systems. And it has a flat spectrum. Generally, the thermal noise is a white noise. Clutter. The clutter is no white generally, and the clutter reflections are specifically in urban scenarios. They are echoes coming from stationary objects. So they are practically copies of the reference signal without Doppler shift, because this reflection come from stationary object, buildings, typically, or also trees and so on. It is possible that actually they are not fully stationary. They have a small Doppler frequency. This is can be if there is some wind and then the branches of the trees move for the blowing of the wind, or if we use the passive radars on the sea. In this case, there are the sea waves, so the sea is not still. It means that the clutter has some internal movement, so there is some Doppler shift in the clutter. Okay, so it is possible that there is some spread in the Doppler domain. Generally, in our analysis, in our signal processing algorithm that we are going to see, we consider that the clutter is either stationary, so practically the Doppler frequency is zero, or there is a little bit of broadening of the spectrum, but the bandwidth of the spectrum is much lower than the Doppler frequency of the target that we want to detect. So this is the fundamental, the assumption that we do, that is quite realistic in many scenarios. for canceling the direct path interference and the clutter itself. Of course, also the direct part interference has no delay and specifically no Doppler shift. Why? Because it comes from an antenna, from a platform that is still. This is what the scenario that we are analyzing. Since the beginning, we said the receiver and the transmitters are still, so only the targets are moving. So the direct path interference has a Doppler shift that is equal to 0. These are fundamental characteristics because they are used in the cancellation algorithm in order to separate the direct path interference, the clutter, from the signal coming from the moving targets. Then we have also the target echoes. The target echoes comes from moving targets, can be aircrafts, ships, or other vehicles. Then the echoes, so the signal coming from the targets, are Doppler shifted, unless of course the target is moving tangentially to the bistatic ellipsoid, but I mean this is a specific case, and anyway, over time the Doppler frequency changes. And then we have the noise that the thermal noise is I mean is non-negligible this is typically a large component at microwave frequency, so in the C, S, and X bands. When we go at lower frequencies, so UHF and VHF, together with the thermal noise, sometimes we can find also man-made noise that coming from other sources, other EM sources, man-made. Okay, so depending on the frequency in which we are working, the noise can have different component. But anyway, in our derivation now, we suppose that our noise is only thermal noise. Now, let's see how we can cancel the disturbance. So how can we clean in some way the surveillance channel in order to detect the target? So let's see the model of the surveillance channel. In the surveillance channel, we have, first of all, the targets. So the second contribution is the sum between 1 and NT. So we have NT targets that we are illuminated. Each of the NT target contributes with a copy of the transmitted signal, delayed by tau m. This tau m is the bistatic delay, so it depends on the bistatic distance range of the target, multiplied by the complex amplitude A sub m. So this is the is related to the radar cross-section of the target and the distance of the target and the usual parameters that characterize also the amplitude in the monostatic case. And then we have the Doppler shift, of course. This is a bistatic Doppler shift. So each target can have a different Doppler shift, a different delay, and a different amplitude, okay? Then let's look at the third term. The third term is the clutter. So we have NC sources of clutter, where if the clutter is stationary, then the Doppler frequency of each component is 0. So you see that there is no the exponential term multiplying each component of the clutter. But each component of the clutter has a delay tau Ci and an amplitude Ci. So in the case of non-stationary clutter, so when the clutter is moving, then it's possible that we need to consider also Doppler shift, as you can see in the box where we have a Ci of t, and you see that we have a component with some Doppler shift or Doppler spreading, okay? Then we have the thermal noise, that is the last term. Now, let's look at the first term that we have in the surveillance signal. That is the direct signal. And these are a delay that is 0 and amplitude that is A sub CERN. And this is a very strong component. We have seen yesterday that actually the direct path to signal power ratio can be 100 dB. So that means that the direct signal is very strong in the surveillance signal. Okay. Now, and we need to cancel it before any building of the ambiguity function. Then let's look at what we have in the reference channel. In the reference channel, we have, of course, the direct signal, dt, that is multiplied by a ref, so another amplitude. Also in this case, a ref is quite high, but we need to have it a clear reference channel. And in this case, we consider that in the reference channel, there is only the noise. We suppose that in the reference channel, both the target and the clutter contributions are negligible. Now, what we do, we sample the surveillance signal and we sample also the reference signal because we, first of all, we want to calculate the ambiguity function, but before that, we need to clean the surveillance channel. So we based our observation on the fact that the useful signal, so the target contributions, have certain Doppler frequency. The direct signal has a Doppler frequency that is 0. We're supposed to have a stationary clutter, so with a Doppler is equal to 0, or a clutter with Doppler spreading, but with a very narrow bandwidth. So the Doppler frequency of the target is much higher than the bandwidth of this or the Doppler spreading. And what we do, so we have here the surveillance sampled signal on one channel. On the other channel, we have the reference signal. And what we do, practically, the main difference between the surveillance signal and the reference signal in the component are the targets with a certain Doppler frequency. So the difference is that in the reference signal, we have a Doppler frequency that is 0. In the surveillance, we have some component with a Doppler frequency that is 0, but some component with a Doppler frequency that is not 0. So suppose that we have these two channels, then we want to build an adaptive filter so that the difference between the surveillance and the reference signal after adaptive filter is a signal SD, that is the residual, and then we want to build this filter in order, the coefficient of this filter, in order to minimize the power of ST. What does it mean? It means that if we minimize the residual signal, it means that in the residual signal, we leave only or almost only the component with a Doppler frequency that is no zero, because the reference signal is at zero Doppler frequency. So if we subtract to the surveillance signal a linear combination of the samples of the reference signal, this is the adaptive filter, is a linear filter. Then if you add a linear combination of the reference signal to the surveillance signal, the only thing that we can do is canceling the component with the same Doppler frequency as the reference signal. The reference signal has a Doppler frequency equal to zero. So practically what this adaptive filter is trying to do is building, using the reference signal, the echo in the surveillance signal that have a Doppler frequency that is equal to zero. In this way, what remains at the output of the difference between the two signals is only, or would be only, the signal with a Doppler frequency that is no zero. And this is what we want to have, because this signal practically is the echo coming from the targets. So this is the main principle. We are trying to cancel through this operation the component in the surveillance signal with a Doppler frequency that is zero or close to zero. If in the surveillance channel we have a clutter with a small Doppler frequency, okay? But we want to leave in the reference, in the surveillance channel, the signals with a Doppler frequency that is no zero, because these components are related to the target echoes. So this is the main principle, okay? This is quite important. We need to understand that. Now, let's see how we can build this adaptive filter. So we assume that multipath and clutter echoes are backscattered from the first K range bins. So the power of the clutter and the multipath is strong in the first range bins. When we go too far, then the power of the clutter as multipath is much lower. So we look at only at these K range bins, and we use the signal model so the signal model is exploited by searching for a minimum residual signal power after cancellation of the disturbance. So disturbance is the direct signal and the echoes. In this case, we consider the ground echoes if you are on a ground scenario. So see here the equation that we have. We want to find alpha. Alpha is the vector of weights in the adaptive filter. And we have the difference between the surveillance signal, S-serve, that is the upper channel, minus a linear combination of the reference signal, we will see how this vector, this matrix X is built. So X times alpha, of course, is a vector. So X times alpha is a linear combination of the multiple copies of the reference signals. You will see they are also shifted in a Doppler, only for very small Doppler. And we subtract these copies of the reference signal to the surveillance signal in order to minimize the power of the residual. Okay, so we need to find this vector or coefficient alpha that are the weights of the adaptive field. Okay, so this is the point. This is called least square approach. How we build X. Okay, B, that is the first matrix, is a matrix that select only the last n rows of the following matrix. So B is a matrix that select the n rows of the matrix lambda minus p times s ref and so on. Okay, so this is just to take n samples, n rows. Now, how is the matrix S ref built? Practically, S ref is a matrix where we put, first of all, the reference signal, S ref. Then we delay the S ref, okay? So D is a permutation matrix. It means that we introduce a delay of one range bin. D squared is a delay of two range bins. Up to dk minus 1 is the delay of k range bins. We say that we consider only k, the first k range bins. Okay, this is the matrix S ref. Now let's see, there is also lambda minus p, lambda minus p plus 1, lambda minus 1, and so on. What is this matrix? This matrix is diagonal and it introduces some Doppler shift in the signal S ref. Okay, so practically we subtract to the vector S surv, so the surveillance signal, all the copies of the reference signal delayed, okay, and multiplied by some Doppler frequency. So we are subtracting to see the surveillance signal, delayed copy of the signal, okay, and we introduce some Doppler shift that is quite small. So we are just subtracting the components of the clutter with a very small Doppler frequency. It means that at the end, the difference S sub minus X alpha is just should contain mainly the components, okay, with a high Doppler shift. The components with high Doppler shift are the components of the signal, the echo of the signal, the targets that we want to detect. This algorithm is called ECA, Extensive Cancellation Algorithm. It has been introduced in 2009 in the paper that you see cited here at the bottom of the slide. Okay. So at this point, let's see, the solution of this minimization problem is something that is standard in signal processing. So the coefficient alpha is this one. So this is the solution of the minimization problem. So minimization problem is that we want to minimize the norm of this difference between these two vectors with respect to alpha. Then the solution alpha of this vector that minimized the norm, so the power of this vector, is this one. X and median times x minus 1 times x and median s sub. Okay? So the residual, that the output, the residual is this one, SDN, that here is called SECA because it's the output of the adaptive filter with this algorithm, is practically this one. We have simply replaced alpha with this expression. And then we have P times S, where P is the big matrix I of n, x minus, etc. Okay, so we build in this way the new signal. I show you some a preliminary result, then I will go into details, but now we have a break. So you see here that we have a map of the on the x-axis we have the bistatic range, and on the y-axis we have the bistatic velocity. So you see that here you cannot recognize whether there is a target or not, and also where is the clutter. Okay, so in the first image, we consider k equal to 50 a range cell, okay, and p is equal to 0. It means that we setting p equal to 0. P equal to 0, it means that the matrix X actually is composed only of the matrix S ref, so only 50 delayed copies of the reference signal. There is no any Doppler shift. And then you see here that the image is changed because we have canceled partially the clutter, okay? And here we do with p k equal to 40 and p equal to 1. So we are subtracting also the component with a small Doppler frequency. Still, on the three first images, we don't know exactly where the clutter is and when the target is, but we see something in the image.
Excuse me, ma'am.
Yeah?
Shall we have the break now?
Yeah. We have the break now. I'm just saying that we will see when we apply the CFAR, CFAR techniques or other techniques, CFAR techniques, that we will detect the targets. Now we have the break, 15 minutes, and then we will go back in 15
Thank you,
minutes.
ma'am.
In 1 minute, I will start.
Yes, ma'am. Ma'am, we can start now.
Okay, perfect. Okay, so we have seen how the ECA works, at least in building, in canceling part of the clutter and the direct the DPI. Now let's go ahead and see how we perform the detection and the tracking. Here you see an example of final results of the tracking. This is just an example with the FM radio station. And here in this experiment, this analysis, there were K equal to 140 range cells used for cancellation. And here the PFA is equal to 10 to minus 4, and the coherent processing interval is 1 second. And you see that in red, the detections, and in the black the ground truth. So that were the tracks of the target, the real targets. And you see in the red that, I mean, the passive radar was able to detect correctly, in many cases, the position of the target. There are also false alarms, as you can see, and a missing detection, but this is normal also in active radars. Anyway, this is just an example. Now let's go to the other block, that is the signal conditioning. Why the signal conditioning? And what is the signal conditioning? The signal conditioning generally is a channel equalization, removal of the unwanted structure in digital signals, or complete reconstruction from the received digital signal. So the reference, this signal condition is a way to build a clear reference signal, but also to make it suitable for the radar, for the sensing application. Because we have seen that in some cases, these are reference signal as pilots or periodic components, and it means that in calculating the ambiguity function, there are many peaks that appear, and these peaks are not targets and can be confused by the radar by targets, so increasing, of course, the number of false alarms in our system. So we need to do this signal conditioning. A typical example that we have seen is the DVB-T signal, because as you can see here in the frame of the VBT, that is an OFTM signals, there are continual pilots that are in blue in the figure upper on the left hand side of the slide. And there are also scattered pilots that are in orange. So the presence of these pilots translate in the ambiguity function in all the peaks that you see in the figure. And you see the 3D image of the ambiguity function, and you see the map on the of the ambiguity function. You see that there are many side lobes, many peaks. All the dotted, black dotted in the map are all peaks that appear in the ambiguity function, and they are not targets, because in this case there is one single target that is in the real in the position 0 0, so 0 Doppler, 0 delay. All the others are peaks due to the shape of the signal. So as you can see from the map, from the ambiguity functions, not easy to recognize the target. Consider that there is always some noise, so it is possible that some of these secondary side lobes, or these side lobes, secondary peaks, are even higher than the signal that is in the position 0 0. So this is not a good ambiguity function for our purposes. So there is this processing of the reference signal, this conditioning of the reference signal, or also the surveillance signal, that I'm not going to explain in details how it is performed. This is just an example to let understand that not all the signals, communication signals, can be used as they are for sensing applications. In some cases, it is necessary first to process the signal before building the ambiguity function, so before the detection. As you can see here, there are some of the blocks that are used for the DVB-T signal. You see guard interval blanking, pilots equalization, pilots blanking. So there are multiple steps that must be done on both the reference channel and the surveillance channel that has the same characteristics. So if you are curious and if you want to see how these algorithms are implemented in detail for the DVB-T signal, then you can look at the paper that is cited at the bottom of the slide, that is dates back to 2005. So there are other papers after that with more efficient algorithm, but the idea is that. And it is also true that some of these algorithms are computationally intensive. Okay, so but they must be performed, otherwise we cannot use it, we cannot perform, we cannot have the ambiguity function. See how in the output of some of these blocks. The first figure is the original ambiguity function. Then there is a second step, that pilot equalization, and the third step, that is residual peaks removal. As you can see, actually, we don't remove all the peaks everywhere, but we try to remove the peaks around the target. So we try to create clear area around the target. That in this case is the green square. Okay, so inside the green square, there is only one peak that is due to the target, and all the others that are due to the pilots are outside this green area. And you see the cut of the ambiguity function A and B. A is the original one, and you see that there is a peak 0, but there are a lot of peaks around. In the B figure, after pilot equalization, residual peaks, removal, and so on, then you see that there is a peak 0. There are other peaks, but around 0, there is a kind of clear area. Okay, so this is principle. So after the I've seen after the signal conditioning, the starbar cancellation, then we perform the cross ambiguity evaluation, and then we need to do the cipher detection. As otherwise, from this map velocity range, we don't get anything. At least we see that there is something, but could be clutter, could be noise, could be targets. So now we need to perform some detection. Now, typically, the techniques that are applied are the uh, very easy, simple cipher techniques that generally are applied on the range Doppler maps. They can be one-dimensional, so they are applied for each Doppler being on the range cells, or sometimes so practically there is a bank of these detectors, each one for each value of the Doppler. Or there are also 2D algorithms that are applied jointly in Doppler and in a range. The easiest one is the CA cipher. CA cipher is the cell averaging. So, since I don't know exactly what you know about this kind of cipher detection, I have added some slides, very few actually, so we can summarize the principle of this kind of cipher detection. So let me explain just this, and then I go back. So there are different ways to apply the 2D cipher. The black cell, the black square is the cell under test. So the cell where we want to detect the target in this map, okay? And then we can take, which is the problem? The problem is that we don't know some of the parameter of the noise, remaining noise. So the power, we don't know the power of the noise. And then what if we don't know the power of the noise, because this is the no parameter, we cannot implement the usual Neumann-Pearson detector. So we need to estimate first the parameter, the noise, then adjust the detection threshold, and then detect the target. How can we estimate the power of the noise? Using the data that we have. The data coming from the surrounding range cells, and in a 2D dimension, also the surrounding Doppler bins. You see here that on the left-hand side, the cell under test is surrounded by a white area. These are the guard cells. I will explain why we use these guard cells. These guard cells are not used for estimating the noise power. Then we have the reference cells that are used for estimating the unknown noise power. This is two-dimensional, so we use kind of rectangle around, or a square around the cell under test. But we can also use a cross-shaped reference window. So as you can see here on the right-hand side, we still have the cell under test in the center, and also the guard cells in both dimensions. The horizontal dimension is the range. The vertical dimension is the frequency. And then we can use the sum sample in the frequency domain, in the close range frequency bins, and some sample in the surrounding range cells to estimate the power of the noise. So how can we implement this? Of course, this is a 2D joint cipher detection, but as I said, actually can be performed on one dimension, frequency bin per frequency bin. It means that suppose that we consider the square in the left-hand side figure, instead of using all the gray cells, gray samples to estimate the power, you work only on the horizontal dimension, and then you move from one horizontal dimension to the other horizontal dimension, because changing the vertical position, so going from the bottom cell to the upper cell, we are moving from one Doppler bin to the other Doppler bin. So each line is a different Doppler bin, okay? So the black cell, the cell under test, is located in a specific Doppler bin and in a specific range cell. And of course, we want to test every range cell in every Doppler bin to be sure to detect all the targets with different Dopplers. So we could apply in one dimension, so only along the horizontal dimension, but each line corresponds to a different Doppler. So then we should apply bank filters working only horizontally, but for each value of Doppler frequency. So let me explain how these one-dimensional cipher detectors can work. Then we have the deconverter is the sampler. So suppose that after the ambiguity function, we have the samples of all the signals. Then the signal conditioning here actually is just to limit the dynamic of the signal. But I mean, we can sometimes it is a logarithm amplifier, but we can ignore it because in many systems there is no any signal conditioning here. And then let's go to the rectifier. The rectifier is a system that built the modulus square of the samples entering, so the inputs, okay? So at the entrance, at the input, sorry, we have these signals, the values, and then I and Q component of the range Doppler map. Then we calculate the modulus square, and then we put it in a shift register. The shift register is the line that you see in the data window and then the cipher window. In the data window, one sample, one new range cell enter, and one range cell exit, okay, from here. So we have the cell under test, CUT, the cut at the center. Then we have GGG that are the guard cells. And then we have the lagging and the leading range cells that we use for estimating the power of the unknown power of the noise. Then we use these cells in some way. You see F hat lead, F hat lag. So we do some processing on these samples. We will see later on what kind of processing we do. Then we combine these two values from the lagging and the leading range cells, and we build this adaptive threshold G hat, okay? Then we multiply this G hat that depends on the data, so it is an adaptive threshold, times alpha. Alpha is a constant, okay? And this constant alpha is fixed based on the probability of false alarm that we want to accept in our system. Then we build the threshold T, and then we compare the sample in the cell under test with this threshold T. Of course, if the cell under test is greater than T, then there is a target. Otherwise, there is no any target. Okay, so what are the hypotheses that we generally do to implement these detectors, particularly all these incoherent CIFAR detectors, but in particular the CA that is the most used in passive radars. We suppose that the interference, so the noise in the reference window, so in the samples surrounding the cell under test, are independent and are identically distributed. It means that if the clutter is Rayleigh Gaussian distributed in the cell under test, it has the same distribution also in the cell surrounding the cell under test. Then we have, of course, we suppose that the clutter is Rayleigh distributed. And, I mean, this is possible because in our system we have already canceled the clutter component, or try to cancel the clutter component, and we are left with some residual of the clutter and with the thermal noise. So we can suppose that these disturbance component are all Gaussian distributed. In I and Q component, it means that the amplitude is Rayleigh distributed. As I already said, the rectifier is a square law, so it makes the square of the amplitude. So the interference, the disturbance at the output of the rectifier is exponential distributed. You should know that if I and Q component are Gaussian distributed, then the amplitude is Rayleigh distributed. The intensity or amplitude square is exponential distributed. Okay, so the mean of the interference power at the output of the rectifier is unknown. So the power of the noise is unknown, and it must be estimated from the samples that are in the reference window. And we make also another hypothesis that the target is modeled as a swirling one. It means that the amplitude is the I and Q component of the amplitude are Gaussian distributed with some power that determines the signal to noise ratio. Now, the first step is to derive, of course, an estimate of the power, that is the average of the interference, using the N reference cells. Now, without going into many details, if the noise is the amplitude square of the noise is exponential distributed, this is the distribution. The parameters that is unknown is exactly sigma squared, so the power, we want to estimate it. So applying a very easy technique for estimating it, that is the maximum likelihood estimate, then we get that sigma squared, the estimate of the sigma square, is the average of the samples coming from the reference cell. So it's 1 over n sum over n of zn. And this is the g, this is the coefficient that we have seen here. See? Okay, so we take all the samples coming from the lagging and the leading range cells. Then we make the average, and this average is G in the CA. CA stands for cell averaging, because we are making the average of the samples, all the samples that are in the CIFAR window, so lagging and leading samples. Then we multiply this G, that is the average, times alpha, that is a constant, and then we have the threshold. So the TCA, the threshold, is the coefficient alpha Ca times the average, so the estimate of the power of the noise. What CFAR means? CFAR stands for constant false alarm rate. So this detector has a probability of false alarm that is constant. Constant with respect to what? Constant with respect to the power of the noise that is unknown. It means that even though we don't know the power of the noise, we estimate it, we build an adaptive threshold, and the probability of the false alarm of this detector does not depend on the unknown parameters. It means that we can fix the alpha Ca coefficient without knowing the power of the noise. As a matter of fact, with this detector, the PFA, the probability of false alarm, is equal to 1 plus alpha Ca divided by n, elevated to minus n. What is n? N is the number of samples coming from the secondary cells, so the surrounding range cells, used for estimating the power of the noise. So this N is that, the number of cells that we use for estimating the power. As you can see here in the expression of the PFA, there is not the power, the unknown power of the noise. So we can fix the threshold simply fixing the PFA. So if you say I want a PFA that is 10 to minus 4, then I invert this equation, replacing PFA equal 10 to minus 4, and then I calculate the alpha, depending on n, the number of pulses that I want to integrate. Okay, I want to use for estimating the power of the noise. Then I can fix the threshold, I can fix the coefficient alpha, and then I can build my detector. Of course, the probability of detection depends on the signal to noise ratio, this real signal to noise ratio. As you can see here, the expression of the probability of false alarm depends on alpha, the threshold coefficient, and the number of pulses that I use, and the signal to noise ratio. But what is important in these detectors is that the probability of false alarm is constant, so it does not depend on the unknown value of the power. So we can see here what's happening in our detector. In the bottom part of the figure, in black, solid line are the intensity practically, so the square of the amplitude of our samples. Okay, so imagine that you are working on this map. So we say that we are working on a range dimension. It means that for each value of the velocity, okay, so we divide the image in velocity bins or frequency bins, the same. So we consider a horizontal line, so different ranges. And then we test for each velocity all the range cells, okay, to see whether there is a target or not. Okay, so we build this threshold, and then we compare the threshold with the output of the cut, okay, the cell under test. Then these values that you see here are practically the values in the ranges, okay? And then if we know the power of the noise, then we can build the Neumann-Pearson detector. And the threshold in the Neumann-Pearson detector is constant. You see, it is the dotted line around minus 10 dBs. See, this is the the threshold for the Neumann-Pearson detector. But we don't know the power, so we needed to estimate it, and we multiply this estimation times alpha. So you see that the solid line close to the dotted line is the threshold for the CA CFAR detector. Okay, just a second. You have to stop 1 second. Okay, now you see that this threshold goes up and down. This is because it depends on the data and then on the estimation of the power. If the power increases instantaneously, then the threshold increases. Now, here we have n equal to 40, so the number of pulses or range cells that are used for estimating the power are 40, so 20 before the cell under test and 20 after the cell under test. And you see that here you have n sub g equal to 20. It means that there are 20 guard cells, 10 before the cell under test and 10 after the cell under test. The threshold, so the coefficient alpha, has been fixed for a probability of false alarm that is 10 to minus 4. We have only a single target that is placed in the range bin number 500. And the signal to noise ratio here is 20 dB. Can you see the shape, the strange shape of the threshold close to the cell under test? You see that actually you have a kind of two towers here, one before the cell under test and the other one after the cell under test. This is because when you test, for instance, the cell under test 480, okay, when the cell under test is 480, in your CFAR window, so in the samples that you use for estimating the power, there is also the target, and the target increases the threshold. That's why. And this happens also when you are after the position of the range cell. So suppose that you are looking at the range being 520. Then again, in the CFAR window that you use to estimate the threshold, so the power of the noise, again, you have a target. And that's why you see this increasing of the threshold, okay? But we are fortunate here because we have only one single target, okay? And you understand that there could be a problem if we have a small target before or after this very strong target here, because in this case, since the threshold increases, if the target is not enough powerful, then the sample does not overcome the threshold, and then we don't see it, okay? But now let's stay with a single target in our map, and then we see the target here with a varying threshold based on the estimation of the power. Now, of course, nothing comes for free. So we can build this adaptive detector, CFAR detector, with a probability of false alarm that is constant with respect to the unknown power of the noise. But this adaptivity means loss. In which sense? They are defined as a CFAR loss. The definition of the CFAR loss is the ratio between the signal to noise ratio necessary in this constant false alarm rate detector divided by the signal to noise ratio in the Neumann-Pearson detector. Remember, on the Neumann-Pearson detector, we know everything. So we know the power of the noise. Then we can set a fixed threshold, as we have seen here, the dotted line. In the cipher detection, we don't know the power. We are estimating the power. So let's suppose that we want to have a specific probability of detection for a set probability of false alarm and for a certain number of cells or samples that we use for estimating the noise power. Then we compare the signal to noise ratio in the cipher detector that is necessary to get for that specific probability false or alarm, the probability of detection that we want. And then we compare it with the signal to noise ratio that is necessary in the Neumann-Pearson detector for the same PD and PFA, okay? So the solid line here relates to the Neumann-Pearson detector, where everything is known. I mean, this ratio is linear. If you go with the logarithm, so if we measure the signal to noise ratio in dB, of course, the losses are the difference between the signal noise ratio in dB for the cipher and the signal to noise ratio in dB for the Neumann-Pearson detector. You see here that if we want to have a PD that is 0.9, okay, and a PFA that is 10 to minus 4, and then we have a number of cells that we use for estimating the power that is 16, then the difference in a dB for getting the same performance is almost 2 dBs, okay? The dotted line is the probability of detection as a function of the signal to noise ratio in the CA cipher detector. The solid line is for the Neumann-Pearson detector. As you can see, for the Neumann-Pearson detector, we need a smaller signal to noise ratio to get PD equal to 0.9. Practically, we need, let's say, a little bit more than 19.5, say, dB. For the CA cipher detectors, we need about 2 extra dBs, so higher signal to noise ratio to get the same performance. This is because our detector is adaptive, so we pay this adaptivity and the cipher property, okay, with this increasing in the signal to noise ratio. Now, let's look here at how the signal, the losses in the cipher detectors changes with the dimension of the cipher window, so the number of samples that we use for estimating the unknown power of the noise. And you see here 3 curves for different values of the probability of false alarm. The highest is for 10 to minus 8, then we have 10 to minus 6, and 10 to minus 4. On the x-axis, you see the dimension of the cipher window from 10 samples to 60 samples. And on the y-axis, you see the cipher losses from 0 dB to 5 dB. And then you see that increasing the dimension of the cipher window, so increasing the number of samples that we use for estimating the power, the losses, the cipher losses, decrease. I mean, this should be expected because increasing the number of samples that we use for estimating the power, the estimate of the power gets better and better. So closer to the true value of the power of the noise. So the losses in the adaptivity decreases, okay? So increasing the number of samples that we use for the power, for estimating the power, then we improve the power estimate, and then we decrease the CFAR loss. So now maybe the idea could be, okay, since I want to decrease the CFAR losses, then I should increase, I should consider a very high value of the CFAR window. The problem is that this is not realistic. And then I will explain why later on. And then the typical number of reference cells that we use is from 20 to 40. So going back to this image that we have here, to estimate the power of the noise along different velocity bins and using different ranges, then we set the cell under test, and then we take no more than 20 cells before the cell under test and 20 cells after the cell under test. We don't increase the value of the range cells, the samples that we consider, to infinite or very high, okay? Now, let's go back to the towers that we see here and what I have said, that actually we noticed here that when in the CFAR window there is a spurious target, so a target in a close position, then the threshold increases. And then if we have a small target, less powerful than the close one, then it is possible that the most powerful target masks the weaker target. Let's go here and we see what happens. See here we have n equal to 20, so we use only 20 samples for estimating the noise power. And then we have 16 guard cells. Again, the probability of false alarm is 10 to minus 4. And here, the signal to noise ratio is 20 dB. Okay, this is the average. But look, we have a strong target, and then that is around 100, position 109, 110. And then we have a weaker target in position 100, okay? So due to the presence of the strong target in 110, when we calculate the threshold in the cell under test 100, then the threshold increases, see? And then the amplitude of the target is smaller than the threshold. Then the dotted line is again the Norman-Pearson threshold, when we know perfectly the power of the noise. In this case, the threshold is fixed, and then we see both targets. But when we don't know the power and we estimated with the CA-CFAR technique, then you see that the stronger target masks the weaker target. This phenomenon is called mutual target masking, okay? So this is possible when there are two targets that are two or even more targets that are close each other, and then one target, the most powerful target, masks the weaker targets. Now, there is also another case that we should consider. So far, we have only considered point-like targets. So targets that occupy a single range cells. But as you can see here in this image, you see that actually some of the targets occupy more than one single range cells. You see that they are longer than one single range cell. Okay, so these are called extended targets. They are not anymore point-like targets. They are extended targets. Okay, so they occupy more than one range cell. Now, in presence of these extended targets, the guard cells are fundamental, because if we don't have these guard cells, we have the phenomenon that is called self-masking. So the same target masks itself. Let's see what happens. Here you see again n equal to 20, so we use 20 range cells to estimate the power. You see again the Neumann-Pearson threshold that is fixed. And you see the CA-CFA threshold that is the solid line, okay? And you see that the target occupies 5 range cells around the 500 range bin, okay? So it is not a point-like, but it is extended target. Here, we are not using any guard cells. Remember, guard cells, as you can see here in the figure, are the cells immediately surrounding the cell under test, okay? In the figures that we have seen so far, we were considering these guard cells. So we were taking, for estimating the power, only these samples, okay? So skipping these samples, the guard cells before and after the cell under test, and taking all these values and these values. So here in the figures that we look at, there are the range cells, the guard cells. There are 20, and here there are 16, okay? Here, there are no guard cells. And you see that the threshold increases, and it is so high in this case that the target masks itself. So the target does not overcome the threshold, okay? This is called self-masking. And this is because we don't have guard cells, okay? So in calculating the power of the noise, suppose that we are here in the position of 500. If we take 10 range cells before and 10 range cells after the position of 500, we are considering also these samples of the target, So the threshold increases and masks the target itself, okay? So we have the self-masking. Now, same situation, same target, but in this case, we use 16 guard cells, 8 before and 8 after, okay? So you see that we have again the behavior of the twin towers with the hole in between. And due to the presence of the guard cells, we are able to detect the target, the extended target. So now you understand why we always consider the guard cells in evaluating the threshold, the CAC threshold. So how can we fix the number of the guard cell? It depends on the maximum dimension of the target that we expect in terms of range cells. So if our target, the longest target that we have, can occupy, say, 5 range cells, then the number of guard cells should be at least 5 before the target and 5 after the target. So 10 range cells. Okay, so this is the minimum that we can have. So the number of guard cells that we can set is related to the dimension of the maximum target. Now, I told you that increasing n, so the number of samples that we have for estimating the power, then we improve the detection, so we decrease the losses. But I told you we cannot increase to very high values this number. Why? Because in the behavior of the CA, in the assumption that we have made at the beginning, we suppose that the interference in the reference window and the cell under tests are independent and identical distributed. It means that if your cell under test is on the C, all the other samples come from range cells in the C. But for instance, if you increase the number of range cells, so the number of samples, maybe in your CFAR window, you can have some part of the cost, for instance, if you are close to the coast of the sea. Then the disturbance is not identically distributed anymore in all the reference windows. Then also we suppose that there are no spurious targets. Well, if you increase the number of range cells that you use, you increase also the probability of having some spurious targets in the reference window. So you increase the probability of being in the condition of the mutual target masking. That's why we cannot increase to infinite the number of cells that we use for estimating the power. Okay, so we have some condition on the number of pulses, the samples that we use for estimating the power, 20 to 40, and we have also some condition on the number of range cell or the guard cells that we have, that is related to the maximum dimension of the target that we are expecting. Now, let's look at another phenomenon that can happen in our scenario. It is possible that we have what is called clutter age. Clutter age means that we have this jump in the power of the clutter. So the clutter is anyway with the same distribution, so exponential distributed, but we have two different areas. In the first area, we have a certain power, and in the other area, we have another power. Remember, we have said that the DCA CFAR works well when the samples in the disturbance samples, the interference samples are all identically distributed. Here, they are not identically distributed because we have this change in the power. So they are all exponential distributed, but we have two areas, so two values of the power. What happens? See here that we apply the cell average, and then when all the cells are in the low power region, then we have a low threshold. When all the cells are in the high power region, then we have a high threshold. What happens in the transition? What happens on the edge? You see that at some point, the threshold starts increasing, and then it reaches the high value. But if you have a target here, whether say in the area between 480 and 500, okay, range bins, if you have a target here, a small target, you don't see it because the threshold is increasing, because in the second area there is a high power target clutter. Here we are in the transition, so we still have low power of the clutter, of the noise, but the threshold is influenced by the high level in the second area. So it means that here, if you have a weak target, you don't see it. And what happened in the resolution beings between, say, 500 and 520 or 530, that you have a high noise power, but the threshold is still not that high because it is influenced by the previous area where the power is low. So here, if you have a spike in the disturbance, then you have a false alarm. So in the clutter age, in the low area, you have a decreasing of the probability of detection. In the high power area, you have a increasing of the probability of false alarm. Okay, now we stop here. We we make the long break, half an hour break, and then we go back in 30 minutes to see how we can solve this problem of the clutter range using the greatest of Go cipher. Okay? See you in half an hour.
Thank you, ma'am.
2 minutes, then we will start. Yes. Okay, I think I can start this last part of the lecture today. So we have seen that we have this problem with in the clutter age where the power is low, we have it in a decrease in the probability of detection, and in the where the power is high, we have an increase in of the probability of false alarm. So for solving this problem, actually, there is another detector, CIFAR detector, that can be used in the greatest of. How it works? The greatest of CIFAR, instead of making the average of all the samples surrounding the cell-hardened test, it makes two different average. One on the lagging samples and one on the leading samples. As you can see here, we have two average. One is on n divided by 2 samples, and the other one n divided by 2. These are the lagging and these are the leading cells. So go greatest of, because between the two average, the G is set choosing the maximum of the two, okay? So instead of having the average on all the n cells, we have two averages and we take the maximum of the two for the G coefficient. In a homogeneous clutter, as you can see, the probability of false alarm for the Go cipher does not depend on the power of the noise, but also only on the coefficient alpha and the number of samples that are used for estimating the power itself. Now let's look at the plot that is quite similar to the previous one. And you see the clutter edge here. So the changes in power between the low part and the high part. And you see that in a dotted line is the cell averaging. The solid line is the greatest of. And you see that here we have a higher threshold. In this way, the probability of false alarm is not increased in this area, in this transition area here. Okay, so the threshold with the greatest of tends to track the higher reflectivity region. Now let's look at the performance in homogeneous clutter. So when there is no any clutter edge, and we see the Neumann-Pearson detector, it is the best one because it knows everything. And we have n equal to 16, so 16 cells, ng equal to 16, the range cells, and here the probability of false alarm is 10 to minus 6. Then we have the Neumann-Pearson detector, the solid black line. Then we have the solid light gray line that is the cell averaging, okay, that is the closest to the Neumann-Pearson, but we know that we have some losses due to the adaptivity. Then we have the dark gray line, solid again, that is the Go cipher, that is this one quite close to the CA. And then here we have another detector that is called the smallest of, is the SAW cipher. How it works? The smallest of is similar to the greatest of, to the Go. So it uses two averages, but instead of choosing the maximum of the two, it chooses the minimum of the two. Why this? Because you have seen that here we have two areas actually. In one area where the power is low, where we decrease the probability of detection. The area where the power is high, then we increase the probability of false alarm. The Go cipher mitigate the problem of the increasing of the probability of false alarm in the high power region. The SAW, the smallest of, mitigate the decreasing of the probability of detection in the low power region. That's why we have also the smallest of. But as you can see in the homogeneous clutter, so when the clutter has not any age, the probability of the SAW cipher are much lower than the probability, the performance of the Neumann-Pearson detector. So the SAW detector is used very rarely. The two detectors that are used in this situation, the cell averaging and the cell averaging and the Go cipher. Okay. Now, what happens when we have multiple targets? So the case that we have seen here, okay, the mutual target masking. We have seen that the CA cipher fails in detecting the weaker target. So which detector can we use in this case? In this case, the detector that can be used is the ordered statistic cipher. The ordered statistics CIFAR practically ranks the n samples in the CIFAR window, and from the smallest to the greatest. Okay, so you see zeta 1 less than zeta 2, smaller than the others. Okay, so they are ranked in increasing ascending order, and it selects as a G instead of the average the kth sample in the window. So you see that GOS is the kth sample, so Z sub K. And why this idea? This idea is because when there is a target, the amplitude of the sample is larger than the amplitude of the sample when there is only noise. So if you rank the samples and you take the kth, it means that all the samples that are greatest than the kth are supposed to contain spurious targets, okay? So in this way, you are able to reject n minus k interfering targets. And this way, the OS CIFAR is able to suppress the mutual target masking. So the OS CIFAR is used when the probability of having many targets in the same scene is not negligible, and the targets are also close each other. Okay. So let's see here the probability of false alarm of the OS CIFAR is what you see in the equation. So it depends on the number of pulses n in the window, the position of k of the sample that we use, and of course the coefficient alpha. Look at the figure. Ignore the censored, so the dotted line, because this is another CIFAR detector that we are not considering. We are considering only the cell averaging and the order statistic. As you can see in the cell averaging, you have the solid line and you have the mutual masking. So the strongest target masks the weak target. But with the order statistic, that is the solid gray line, then it is there is no this masking, and you see that both samples, so both targets, overcome the threshold, the gray solid line, the threshold of the order statistic, and then we see both targets. So in this way, we mitigate the effect of mutual masking on one target, the strong target, on the other target. Okay. Now, we have finished all the principal CIFAR algorithm that are used, the main algorithm that are used in detection for passive radar on the map, range velocity map. Then, of course, after detection, we have the tracking. And the tracking normally is performed used either the Kalman filter or the extended Kalman filter. Okay. Now, before going to some example also for the tracking, we can observe that unless we have very narrow beam for the targets that are in some specific direction of arrival, here we don't have angle information. We have only bistatic range and Doppler plane. Keep the ambiguity function provide us with information only on the Doppler and on the range. How can we get the information on the angle? We could perform at the level of the antenna, the receiving antenna of the surveillance channel, we could perform some beamforming. So in this way, we focus the antenna in a specific direction, and we could also scan the field of view electronically, so changing the phases of each antenna in order to move the form and move the beam. On the receive, we can do this on receive before the signal conditioning and so on. So in some system, the classical configuration for the estimation of the direction of arrival is the uniform linear array. Okay. Unfortunately, we know that when we use the uniformly linear array, the resolution in angle is quite good when we are close to the bore site, say in a field of view that is minus 60 degrees plus 60 degrees. But when we are close to the end fire, so when you are close to minus 90 degrees or plus 90 degrees, then the beam width increases, and this is a great disadvantage in passive radars, because we want to see in all directions. Okay. But still, and we will see that actually to mitigate this problem in many passive systems use a circular linear, circular uniform array, and we will see how. But there are systems that use the ULA, so the uniform linear array, in particular when they scan only a specific angle sector. For instance, the Dahlia system developed the Fraunhofer in Germany use a ULA, so a uniform linear array. So let's summarize how we can form the beam. So in a uniform linear array when we have n elements. So we suppose that each of the n elements are omnidirectional, and they have the same sensitivity, and we suppose to know perfectly the characteristic of each antenna, each element. So the antenna is calibrated. And you see that in a uniform linear array, the distance between the elements is the same, is d. The bore site is the direction orthogonal to the array. And then we have the angle of the direction of arrival of the signal, that is theta. And lambda is the wavelength of the signal. That is, of course, it depends on the lambda, depends on the signal that has been transmitted by the source of opportunity. Okay, so suppose that the signal that has been transmitted is A, that's constant, and then it has been transmitted on a certain carrier frequency that f sub 0. Now this signal arrive to the element, to all the elements of the antenna, and suppose that our reference element is the first one, so that is with the index 0. We have n elements from 0 to n minus 1. So we suppose that we are in a far field. It means that the propagation is a plane wave propagation. But there is a difference in the propagation path between one element and the other element because of the distance between the elements on the antenna. And then the received signal, of course, is at some it is at the carrier frequency f sub 0. We are supposing that in this case the target is still, so we don't have Doppler, a different Doppler frequency. And you see here that actually we have a delay that depends on the position of the antenna. So it depends on the direction of arrival of the signal through the angle theta, the position of the antenna, that is d, and the distance between one antenna and the other antenna, that is d. Then there is an initial phase. Actually, we don't care too much about this initial phase. We care only about the differences between one element of the antenna and the other element of the antenna. So we see, we sample the signal at t sub 0 on each element. N is the index of the elements of the antenna. And then we replace t with t sub 0 because we are sampling the signal. Then we put outside all the elements all the terms that do not depend on the position of the antenna. So we have e to j phi 0 sub 0 because this is the same for all the elements of the antenna. And then we have this exponential that takes into account the carrier frequency. Again, the same for all the elements of the antenna. And we put everything in the complex coefficient a hat, okay? Here, this exponential term depend on d and depend on theta, and that's why it is outside. Now we assemble all the n samples on each element of the antenna, and we call it snapshot. So the snapshot is a kind of photography, so the sampling at a specific time instant on all the elements of the antenna. So it is a vector n dimensional vector. So S0, S1, Sn minus 1, okay? So we have this common element that is a hat, that is complex. And then we have all these exponential term here, okay, that depends on the index n, so the position of the antenna, okay? So we have 1 minus j 2 pi d sin theta divided by lambda and so on. So a theta is this vector with this very specific shape, and it is called spatial steering vector and can be written in this way. Now, we in many cases use this definition. We call d sin theta divided by lambda as spatial frequency, okay? And in this way, our spatial steering vector has almost the same shape as the temporal steering vector that we use in many cases in detection in the radar. So this is a spatial. Why is spatial? Spatial because it is on contains the samples on all the elements of the antenna that are spatially separated. That's why this is a spatial steering vector, okay? So how we do beamforming? If there is no any phase shifter at the output of each element of the antenna, what we do? We sum together the output of each antenna, and the output of each antenna is we have seen, I mean, there is the noise, but for a second, neglect the presence of the noise. We have the sum of all these samples all together. So if we sum all these samples, we have something that is proportional to 1 over n, sum n from 0 to n minus 1 of these exponential terms. Here you see this is the original formulation, and here I put the spatial frequency. This is the signal that we have, and it depends on the direction of arrival of the signal theta. The beam pattern of the antenna is defined as the power of the signal. So modulus squared of FB of theta. Okay, so let's calculate the power of this signal, as you can see, and then making some easy calculation on that, we get that the beam pattern has this shape. Sinc function of d lambda sin theta times n divide sinc d lambda sin theta modulo squared. Okay, they are very similar function, but you should notice that here we have n in the argument. We don't have the n, but they depends on the angle theta. So the beam pattern is independent of the temporal waveform of the signal, okay? It has a, if we don't put any phase shifter, then the maximum of the beam pattern, I will show you the plot, is in the both side. So in the direction orthogonal to the line that contains the antenna. So it is at 0 degree. If we want to change the angle, then we need to introduce some phase shifter to move the beam, which is the beam width. The beam width is defined as the angle between the points at which the amplitude of the beam pattern falls to half or by 3 dB. This is the typical definition. So it's a minus 3 dB beam width. And the beam width also indicates the ability to resolve signal sources. So if we do conventional beamforming, so if we don't do anything specific to increase the resolution, then the angle resolution is actually equal to the beam width of the main lobe. Then there are other peaks that are called side lobes. If these side lobes are very high, then it is possible that interfering signals, unwanted signals, can enter into the signal that is being processed by the antenna, and then we have an interference. So the idea is that we should reduce as much as possible the amplitude of the side lobes in order to reduce the interference of the targets that enter, that are not in the main lobe, but are in the side lobes of the antenna. Now the effective array aperture of antenna is defined as the product between n, the element of the antenna, and d, the distance between the elements of the antenna. Now let's see what happens. Here we have 10 isotopic elements. There is no any phase shifting, okay? Any phase. And we are comparing the beam pattern with different values of D. Lambda is the wavelength. So here we have a distance that is lambda fourth. This is lambda over 2, so half lambda. And here the separation is lambda. So it seems that the number of elements is 10, okay? So it seems that going from lambda fourth to lambda over 2, we are increasing the gain, so the height of the main beam, okay? We go from 6 dB to 10 dB. This is because sorry, the gain depends on L, the effective array aperture. Then we can think that even increasing more the distance between the elements, okay, can improve the gain of the antenna. But this is not true, because you see that when D is greater than lambda over 2, the gain is the same, is 10 dB, but we have the creation of these very high side lobes that here we don't see, and these are called grating lobes. So without going into many details, otherwise we need to do a separate multi-hour lectures on array processing. Let's say that D equal to lambda divided by 2, so half wavelength is the best distance, the ideal distance in a uniformly linear array to get the maximum gain of the antenna and the better resolution. You see that here the main beam is much larger than this one. Here we have a narrow main beam, so it seems that we are gaining resolution, but we are losing a lot inside the lobes. So in this situation, this is not the third one, is not a good situation, it's not a good scenario, because we have multiple grating lobes. So we should stay as close as possible to the situation in the middle, where the distance D between the elements is half the wavelength, okay? So now how can we do the conventional beamforming? We have seen the conventional beamforming actually is a spatial linear finite impulse response filtering. Practically, we take the observed snapshot Z and we make a linear combination of the observed vector. In this previous calculation, the weight is equal to practically 1 over n. N, I mean the constant 1 over n, the value of the constant is not fundamental, okay? What is important is that all the elements of this weight W are all equal, okay? So if all the elements are equal, for instance, are equal to 1, then the beamformer passes undistorted the signal with that direction of arrival theta equal to 0. Why? Because the maximum, okay, of the beam pattern is here, is in the 0 direction. Sorry, here there is a slight movement of the axis here, because the maximum should be 0, is in 0. So the x-axis is a little bit misplaced, okay? The maximum should be in a position equal to 0. And attenuates all the signals coming from all the other directions that are different from the bore side. What happens if we want to point our beam in another direction? Because in the passive radar anyway, we want to scan the field of view. So we want to scan different angles, looking for targets in different angle position. Then what should we do? We need to introduce some a different weight W in order to scan the beam. So this is called the beam steering, and it is accomplished using a weight vector W that is similar to the steering vector, but it is pointed in a specific angle of theta sub 0. So let's see what happens. In this case, the beam pattern is given by the output of this filter, so WH times A theta. In the other case, it was 1 over n, so W was equal to 1 over n, okay? Now let's see what happens. We replace W with the expression of similar to A, but in theta 0. So here we have theta 0, and we have the generic theta. Then let's put together the exponentials in this way. Let's do some similar operations, similar to what we have done before, and we come out with a similar expression. See, we have sinc d over lambda, but here we don't have sin theta, but we have sin theta sub 0 minus sin theta times n. And at the denominator, we have sin theta 0 minus sin theta. So if we compare it with this expression, see, here we had only sin theta, sin theta. Here we have a difference of sin. One is in the generic theta, the other one is in theta sub 0, where we want to point the beam. So see what happens. Again, we choose the best distance between the elements. So D is equal to half the wavelength. We have n equal to 16 elements of the antenna. And we want to point the beam along the bore side, so at 0 degrees. See, this is the beam pattern. Beam width and the level of side lobes is about minus 13 dB. Okay, so this is the main lobe pointed towards the bore side, so 0 degrees, and then we have the principal side lobes, the highest, and then we have all the other side lobes in a dB scale. Now, we change the angle, so we point the beam along the direction 20 degrees. Then we put theta 0 here and here. And this is what we have, okay? Then we have angle here in 20 degrees. Now, we pointed at 80 degrees, and we have again this pattern. So if you see that as far as we point the array in an angle that is close, say between a -6 degree and 60 degrees around the bore site, we still have a good main lobe. So with a decent beam width, so a decent resolution in angle. But if you move close to 90 degrees, -90 degrees, and +90 degrees, then the beam pattern is much broader, and then we don't have any more a good resolution in angle, okay? This is the reason why in many practical passive radars, we use a uniform circular array. So you see, this is the circle, and uniform because this distance between the elements D is the same for all the elements of the antenna. And then you see that the radius is R, and we have multiple elements, okay? Why we use the UCA? We use the circular antenna because practically the circular array provides omnidirectional coverage capabilities. So practically the beam are quite similar independently of their direction with respect to the array, okay? So here we have this problem of the broadening of the main beam. And here with the circular array, we don't have this problem. Of course, the equation are a bit more complex compared to this, because here the spatial steering vector is quite easy, as you can see, because it's the antennas are on a line, here are on a circle. So the plot is a bit more complex, but still it is possible to write the steering vector, okay? And then multiple systems, the Cora, the Silent Sentry, Parade, the Aulos, Parade 1, the system of TNO, this system developed by Poland. They have this circular array, so uniform array for their antennas, okay? Generally, the arrays, the passive radars operate at low frequency VHF and UHF more than LSC and X band, okay? When we go too low with the frequency, of course, we need very high dimensional, very high dimensional arrays. And this is also the reason why in some situation we use a multi-static configuration, okay? This is multi-static configuration, as you can see. So let me explain better. If we work at low frequency, the angular resolution is not particularly good. And then if it is not particularly good, then we cannot localize with a high precision the angular position of the target. This is the reason why in some situation or in many situations, we use the multi-static configuration. The typical one is one single receiver and multiple transmitters. But in some cases, we have multiple receiver and multiple transmitters. So we go from a passive bistatic radar to a passive multistatic radar. I'm not going to explain all the details of the multi-static radar. This is outside the scope of this course. I'm just showing you that with multiple systems, we have multiple ellipses. So you see that for the first target, if there is no any angular resolution, and then the target could be whenever on the first ellipse, the same on the second ellipse, and the same on the third ellipse. But these three ellipses have only a common interception, that here is the red star, and it means that the target that they are trying to detect is in the interception. So in this way, the three systems can detect the range position, the Doppler position, and also the angular position. Okay, even though they don't have a, even though each passive channel has no a good angular resolution, putting together multiple channels, so a multi-static system, then we can have a very precise estimate of the direction of arrival, so the position, angular position of the target. Now, let me show you in the next 20 minutes, let me show you an example. Here, practically close to my city, that is Pisa, there is another city that is called Leghorn, in Italian, Livorno. And here we have a UMTS base station. And here in the upper part, we have a FM transmitter, so that is on the Monte Serra, on the Serra Mountain, okay? So one is here in the transmitter, UMTS transmitter is practically at the harbor, and one is on this mountain. And then we have a bistatic passive radar here where there is a receiver, okay? So the antenna gain of the receiver is 10 dB with the angle, a beamwidth of 3 degrees, okay? And then we have FM commercial radio station at 36 kilometers from the receiver, and another one at 400, less than 500 meters away from the receiver. It's a UMTS base station. So now in this situation, we have two different signals of opportunity. So the receiver can choose to use both of them, or can choose to use only one of them. Of course, the geometry is different, and the characteristic of the signals are different. So remember that when the target is crossing the baseline, the geometry is really bad. So the estimation of the Doppler frequency and the range is really bad. So this is an harbor, and the boats enter the harbor practically crossing the baseline between the UMTS transmitter and the receiver. Okay, but you can see there is also another line here on the upper part of the plot, where the receiver is closer to the baseline between the receiver and the FM station. So depending on the different trajectory, we can have a better channel. UMTS could be better, or the FM could be better, at least in terms of geometry. So how can we evaluate the goodness of the geometry? We looked at the accuracy of the range and velocity estimation through the Kramer-Rao bounds. So here we see that if the Kramer-Rao bound is very high, then the accuracy is bad. So we should look at the low value of the Kramer-Rao bound. It is measured in the B. So in the blue area, we have a good estimation of the range. In the green or red area, we have a bad estimation of the range or the velocity. So this is one is for the UMTS signal. And since you see here that the white one is the ground, so the mask of the ground, and all the others is the sea, and of course the sea close to the coast is the harbor. See here in the figure in both left hand side and right hand side that there is an area where you see some red color, okay? It is exactly the area close to the baseline, so the line that is between the receiver and the transmitter. That is bad geometry, so when the target crosses the baseline, the resolution in a range and in velocity gets quite bad, okay? So we should avoid using the UMTS measurement when we are in that area. Of course, when we are close to the coast, so close to the receiver or close to this transmitter, the estimation is good because we have a good range estimation when you are close to the coast. Of course, we have not a good estimation when we are far away from the receiver and the transmitter because we have a low signal to noise ratio. Okay, remember that we have a high signal to noise ratio when either the target is close to the receiver or it is close to the transmitter. Here we are analyzing the performance of the transmitter number one, so the UMTS. Now let's look at the FM measurement. As you can see here in this part of the C, the target is practically quite close to the baseline between the receiver and the transmitter number two. This is the reason why this area is red, because this geometry is bad, at least in terms of range. So when the target is in this area, that here is red, it is not good to use the FM measurement because here the ambiguity function is bad and then we don't get a good estimation of the range and the velocity of the target. So, which is the best channel? In blue, the best channel is the first one, so is the UMTS. In light blue, the best channel is the second one, so the FM. And you see on the map that for range and velocity, practically, we have two different channels. Again, the blue one is the UMTS, the light blue is the FM. And you see that here the geometry has a large impact on the choice of the best channel. Now let's analyze the case of the tracking. And we suppose that there is a target that is entering the harbor. You see here the red line is the trajectory of the target that is entering the harbor. And it is compared with the best channel for range estimation. See? Okay. Now, the model equation, the state equation for the target is this one. X at the time instant k plus 1 is the usual f times xk plus the process noise. F is the transition matrix that characterize the equation, the kinematic equation of the target, and it is this one. The target is characterized by position and velocity in the direction x and y. And this is the noise that is Gaussian with mean value z and covariance matrix q. The measurement, in this case, the measurement actually is not linear because the radar measures the range and the angle. And then we have non-linear measurement of the vector x plus the observation error. The observation error, the noise here, depends on the covariance matrix of the noise, the observation noise. And the covariance matrix of the observation noise depends also on the geometry of the system, not only on the waveform, but also on the geometry of the system. So in some case, it is really bad. Now, without going into many details, because practically the correlation matrix of the noise depends on the Fisher matrix, and the Fisher matrix depends on the previous on the prior information and depends on the new measurement information. What we decide? So practically, we need to decide which channel we want to use at each time instant. We could use always the FM, always the UMTS, or the best of the two. It is clear that if we are crossing the baseline for one of these two channels, it is much better if we use the other one. So all the principle that here we are discussing is exactly this. In choosing the channel, choose the best one. Thus that it has a better resolution and a better accuracy. I'm not explaining the details of this, but I will show you the results. So see here, this is the goodness of the estimation using the sorry, the UMTS channel, okay? And you see that the accuracy in some areas not particularly good. Then FM is the red one. So in some area, the FM is better than UMTS, okay? But in a green one is the selection. So when we choose the best channel among the two, between the two. So see, the green one is the best of the best. This is for the X position. This is for the velocity along X. And we have a similar behavior also for the Y position and for the Y velocity. So when we have multiple sources, multiple signals that we can use, in some cases, due to the geometry, it is better if we select only one of the signal, or if we have more than two, we can select a set of these signals in order to improve the performance of the tracking, instead of using all the channels or always the same channel, because in some situation when the geometry is bad, then we can get bad performance. So at this point, I think that we have the real systems, but I prefer to introduce the real systems tomorrow. Tomorrow we will start with the real system because we have certain number of slides that I want to detail to you. So I prefer not to go through this section. So we can finish the lecture 5 minutes in advance. And if you have any question, now it's time to do it. I will summarize what we have seen today, and then I will give you some minutes for the question. So what we have seen today. Practically today, we have seen the signal processing in the passive radars. There are multiple steps to get the detection and the tracking in the passive radars. First of all, the calculation of the cross-ambiguity function. And since the integration time is quite long, there are many operations that we need to do, and then we need to find an efficient way to implement the cross-ambiguity function calculation. And we have seen mainly two algorithms. One that uses the interpretation of the ambiguity function as the Fourier transform of the product of these two signals. The other one uses the interpretation as the correlation between two signals, and then we use the FFT and then the inverse of the FFT. Then we looked at the one algorithm that is used for the disturbance cancellation, specifically the clutter and the DPI. And this algorithm is based on adaptive filtering, and we have seen the ECA, so the extensive cancellation algorithm, to obtain the estimation. Then we looked at the signal conditioning, frankly, with a few details, only some figure to show that in some cases we need to process the signal before using it in the ambiguity function and in the detection algorithm. And some step of this condition can be computationally intensive, but they are effective. Then we have seen after the cross-ambiguity function how we implemented the detection techniques. And we have seen some of the CIFAR techniques, the CA in particularly, and then all the problems that the CA can face and some of the solution of this problem. We have seen the importance of the guard cells in the extended targets. We have seen the problem of the mutual target masking, so the solution with the OS CIFAR. We have seen the problem of the clutterage and the solution, a possible solution with the greatest of CIFAR. And we have seen also the performance. Then we analyzed the problem of the direction of arrival estimation, and then very basic principle of the direction of arrival, so the beamforming. With the ULA, that's the easiest one, and we have seen how to build, how to steer the main beam towards a specific direction that is different from the bore sight. So we choose the weight, and we have also seen the problem, but I mean, the existence of graded lobes. That's why in a ULA we always choose lambda divided by 2 as a separation between the elements of the antenna. And then these are the figures with different angles. And we have seen also, we have touched upon the problem of the broadening of the beam pattern, the main beam, when we are close to plus minus 90 degrees. This is the reason why in many passive radars we use uniform circular array, okay? And then we have seen also how we can use multiple channels for the DOA estimation in this case, but also for tracking. Then we can use the information coming from multiple receivers and choosing the best channel in order to improve the performance of the tracking. Then we stop here. If there are questions, then you can ask me. Otherwise, we close the lecture and we will see tomorrow afternoon with the real systems in passive radars. and then we will go through the theory of MIMO radars. Is there any question? Again, if you want to ask something, you can also send me emails for curiosity, for explanation, clarification, whatever you want. Is there any question?
Hello, ma'am. I think anyone don't have any question. So
Okay.
shall we close the session now?
Okay, we can close the lecture now and see you tomorrow. Okay?
Okay. Yeah, ma'am. Ma'am, you are the host, so can you end the meeting?
Oh, yes, sure. I am the meeting. Here it
Okay.
is.
Thank you, ma'am.
Bye-bye.